bits I'm thinking more defined in terms of responses. But I hope it's clear why this thing will remain invariant under in truth value under its relative drags. Right, so we come on to indistinguishability. I mean, what I've just said, I think, applies to all of the space-time theories. It even applies to manifold points. You can say two manifold points are distinct from one another by the Hausdorff property. There's various ways that you can, everything I've said carries over to GR. But let's look at indistinguishability, which in some sense is so crucial to ideas of structures over the last century. And I've been sort of, I think battling is the only word for it, with this for a very long time now. And forgive me if you've heard me talk in similar ways before. I think I've got something slightly different to say. But one way of entering into the subject of what is particle indistinguishability in quantum mechanics is think of quantum property ascriptions, and this is in the so-called logical algebraic approach, people like Gauss and that sort of stuff. But I think it's pretty good, and it's fairly natural, at least in non-relativistic quantum theory. So here we've got a projection operator, and I've got this complicated, symmetrized projection operator. The reason I've got to have the 1 minus p's in there, by the way, if I just had identity in there, if I just had projection p tensor product and load of identities plus, and then identity tensor product p tensor product and load of identities, and so on and so forth, that thing wouldn't be identical. Okay, so if you square it, you don't get it back again. So in order to have something which is identical, it kind of counts as a property, then it's got to have this sort of thing. But I'm saying that this goes over to this in classical property description. I'm taking the conjunction is really multiplication of projections. So you're multiplying projections to different systems. So that will just take you to so p times p times put up 1 times 1 minus p. It will give you the compound thing. So that's giving you this set of conjunctions. And then the plus sign is taking this disjunction. This is fairly standard stuff within Lattice theoretic approaches to quantum theory, and as I say, the logical algebraic approach. So this is my guide, if you like, as to how one's going to, in a way, speak in language, convert into language some of the structure that one's got at the level of indistinguishables. And I hope it's kind of clear why this would give you something invariant to this sort of construction. Let me also just give a theorem. This is a simple theorem. It doesn't know how to prove, and I'm sure there's much better ones around. So in general, if you've got a first-order language with identity but without any proper names, the SBNEL sentence satisfiable only in models of cardinality n, that's why I need identity here, but I don't think there's actually a problem with doing this without identity. Then there is a totally symmetric and totally irreflexive n-ray predicate G, such that this is the case. So this is an attempt to translate into linguistic terms the permutation invariance that we see at the level of the state description in quantum mechanics. And this thing, of course, will be invariant under permutations. But, I mean, if you did supplement L with names, keep S without any names, so you introduce names and let them all name distinct things, then actually this equivalent. So I've got any sentence at all with definite categoricals. It's got a definite cardinality of the models in which it's true. But otherwise it would be any sentence in predicate calculus. And it is true if and only if this predication is true, where this thing is totally symmetrized and totally reflexive. Okay, so that sort of really rather persuaded me of the view that in any way follows, if you think about Gibson indistinguishability, that indistinguishability doesn't actually stop you from talking about things being very different from you. It's not the case that everything is somehow similar. Exactly the same, it's exactly the same properties. Absolutely not. And I mean, it's partly trying to understand where does that view come from. That initiated a recent starter project I've been working on, which is just going back to the period from about 1870 to 1925, when the thing was more or less completed. What was quantum indistinguishability? How did it differ from Gibbs' notion of indistinguishability? And how was Gibbs' notion of indistinguishability understood? The simple answer is it wasn't. It just wasn't understood at all. Nobody paid any attention to it. But Gibbs' notion of indistinguishability is really saying, well, I think I've got a slide on it. So if you've got an n-particle state space, Okay, this is what Gibbs calls specific phases. Then you've got n ordered pairs. Each ordered pair is that's a triple of real numbers, another triple of real numbers, and so forth. The point is you've got a sequence, and you can talk about sequence position. And sequence position is really functional as a particle name. The reduced n-particle state space, what Gibbs called the space of generic phase, is quotienting out by the permutation group over n particles. And that's giving you the same set of ordered pairs. It's an unordered set of ordered pairs. Right? So now there is no such thing as sequence position, and there is no name. So really, all that's involved is you're just not giving names to particles, but the particles can be in different locations and having different momentum and so on and so forth. It's really not, in no sense are they alike in all of their properties. The villain in the piece is partly Planck, it's partly Boltzmann, and it's St. Anderson. Because all of those guys, when they spoke about energy units, and of course that's how all of this entered into quantum theory, they spoke about things that were exactly the same. The idea that an energy unit could have a state space of its own was completely beyond their conception. It was beyond Einstein's conception too, which is amazing, because Einstein in 1905, after all, thought that light quanta were localized. So then the light quanta can have different positions in space. And he should have thought, well, why can't they have different momentum? He even had the idea of directionality. But he never had the idea that a light quantum could have a state space of its own. First person to do so? Does anybody know? It's not normally spoken of like this. Does anyone know? It was Bose. And that was Bose's amazing contribution. He thought the light quantum can have a state space, just like a particle can, a material particle. Such a simple observation, such a simple thought, and the guy's immortalized forever for it. Look that we could have simple thoughts. So it was, and Einstein, of course, had no grasp of this. The scales fell from his eyes when he read Bose's short paper in 1924. Okay, and actually it's interesting to ask, what kind of allowed Bose to think that? And one of the things, it's complex. Okay, let me not go into the history, I'll run out of time otherwise. So I've missed the slide, I'm aware of that. Let me just go back to this. So I'm trying to really simplify this and articulate in what sense indistinguishability as such is just not problematic at the level of everyday objects. So I've got Buckbeak flying higher than Pegasus. There it is. Pegasus. And we can formalize that as an asymmetric predicate FAB, A flies higher than B, or A that is a hippogriff that flies higher than B that is a winged horse, or B that is a hippogriff flies higher than A, which is a winged horse. Okay, and as soon as you've done that, and here's this formalization, you've now got a completely symmetrized predicate. Okay, it's a complex predicate. And so that just illustrates what I was saying before. But then, of course, we could just drop the proper names and just say that that which is a hippogriff flies higher than that which is a winged horse, and then you just got this straightforward predicate calculus. And so that's what I've really come to the view of, that just predicate calculus, any description you want to provide in predicate calculus, as long as you don't use any proper names, it's equivalent to indistinguishables. We're all indistinguishables. Okay. So if that's an obvious thought to you, great, and I don't have anything to teach, but if it's not an obvious thought to you, I really stand by it. I mean, we are all indistinguishables in exactly the same way that electrons are indistinguishable from one another. We are indistinguishable from one another. The difference is, of course, we're much more complex systems than electrons. We have much more complex properties, and so forth. I mean, here's a way of thinking about it. The bare particular is like an indistinguishable particle. So, bare particulars get dressed. Elementary particles get to acquire some range of momentum and location and so forth. So, the issue of identifying the permutations, if my bare particular is permuted with your bare particular, nothing has changed. Okay, so it's that sort of thing. Put it in terms of, I don't know if it would help to put it in terms of essence or inanimate, soul or something like that, or vitalistic we've all got the same vitalistic substance, if we've all got the same souls, I know that's not normal, then permeating souls among each other doesn't change anything, permeating whatever, and so forth. So, I mean, you know, in a way, this sort of, you know, people say, this is very much, of course, deflationary reading of indistinguishability. No wonder people have been mystified by it. It's so straightforward and trivial at everyday level with macroscopic objects and so forth. That there's almost just not an issue. Of course, it is an issue not to use proper names, because we do use proper names all the time. So, what's going on with that? So the general idea there, hang on, let me just check if I've got a slide on this. I'm getting ahead of myself. Can I just go back over a bit of the formalism, just to remind you of those things, and then I'll pick up where I just left off. So the basic idea is that the tensor and Cartesian product structure carries with it a proper name, namely the position, the location in the sequence. So the n-particle state space spanned by product states of this form. And I was sort of noticing earlier with Gus's Leakewater's Erasmus talk that every time you had an entry in the tensor product structure, you had a number to give, you know, which element in the tensor product it was, but you didn't need it. Sorry.
Here,
you didn't need it. You know, every single time the number exactly corresponded to the sequence position. So it's just redundant. The sequence position itself gives you a proper name. Okay, and what's happening when you anti-symmetrize or symmetrize is you're essentially eliminating that tensor product, that sequence position from having that function. It can no longer have any such function. And you know, as evidence of that, just take a partial trace with respect to any one of these, trace out everything else, you always get the same thing. Sequence position just means nothing anymore once you symmetrize. And that's, the thought is that that's all that symmetrization does. It just eliminates sequence position. But of course, if you're right, if we can violate that inequalities with mere symmetrized, and this is G and WM, what is it?
GMW entangled.
GMW. So this is a non-GMW entangled state. So if you can violate the Bell's inequality, maybe I can actually think it's possible. So it's a very deflationary reading about what indistinguishability and so on. The huge great difference of quantum theory is you can get superpositions of these guys, and then you've got genuine GMW entanglement, and then all bets are off, depending on the nature of the superposition. If you've just got this sort of trivial entanglement, I can just speak of one-particle states. Just got an unordered set of one-particle states. Okay, so let's see. Let me talk a little bit about what's going on, and again, I guess you've already said a lot of this, but so we individuate particles, supposedly indistinguishable particles, by things like their location. You know, it's the electron in the microscope. You know, it's not the electron in the flask, not a thing that's allowed. So spatial, being constrained to different spatial regions is enough to do it. But if you're asking where does a useful notion of a name come from, well, it's got to be some sort of a property that is stable over time, right? And you know, as long as they're talking about molecules in a gas, atoms, you know, confined, you know, then they will be stable over time. But there may be other kinds of properties that likewise dynamically stable that can be used as proper names. But the thing about these dynamical properties is they better permit an interesting variation still if you're going to have an interesting state space where you can use the dynamical property, the stable dynamical property, to label the particle. And there's an interesting state space. There's a lot of other stuff that this thing with this stable dynamical property, a lot of other properties that you can have. And then you can talk about state space. And of course, that's how it works at the microscopic level. All of us have very stable dynamical properties. It was not written into the shapes of our bodies and the shapes of our faces. It's written into our DNA and into our chromosomes, totally stable dynamical properties. So we can always use that, and we can talk about and assign each other proper names and so forth. And if we're talking about, once you're doing that, of course, you've broken the permutation symmetry. In no sense can you commute my DNA with your DNA and you haven't changed anything? No, changed everything. So, I hope it's clear how that goes. I want to come on to Gibbs paradox. How much is the time? Oh, not well.
Should sort of
not well.
stop at 3 o'clock.
Yeah. I'm sorry, but that's 8 minutes. So I've been deflationary about.
You did start a bit late.
Just perhaps a couple of minutes. So I've been deflationary about indistinguishability, but it doesn't mean that there's no impact. Just classically think of the Gibbs paradox. So who doesn't know what the Gibbs paradox is? Great. Okay, good. So got two different gases, and you allow them to diffuse one into the other. Is there an increase in entropy? Well, if the substances are different, yes, there's an increase in entropy. Very easily calculated. It's very easily measured. Brilliant. And what's going on? This is a space-time diagram of kind of opening the compartment. Really, here the two gases are separated right throughout the period. Here's another two gases, and now the partition just sort of disappears at this time to primed, and then the trajectories penetrate and they mingle and so forth. So that's fine. Now, what happens when the gases are the same? Well, the difference in the final state here and here is really the difference between this state and this state. So, can you see what I've done? I've sort of disentangled them. Here they've sort of gotten tangled up with one another, and now I'm just disentangling one. So this guy that got over here, I'm sticking it back there, which is where it got to here. If you'll notice, this corresponds to that point corresponds to that point. You see, so the state here is exactly the same as the state here. Right? But this state does not look to be the same as this state. So this disentangling. So that's what we think. We think there ought to be an entropy of mixing because we can get this interpenetration of the gases. You know, these trajectories, they're just the same as I mean, the same trajectories as here where we have the mixing. So, how could there not be mixing that's occurred here? So we think there ought to be entropy increase. So Dennis Deeks, who I rather hope actually will come to this one. Anyway, so Dennis Deeks, who I've been arguing about this with for years now, insists that there is an entropy of mixing in all cases, even when the substances are the same. Okay. So, just to simplify, and this is what it comes down to, the Gibbs paradox of two particles. Can the state of two particles be unchanged? So is this state, could it be the same as this state, even though each particle is changed? So simple question. We've got two different things. Each of them changes. Does the pair of things change? Do you think it's a tautology? Yes, if each of two things has changed, the two things must have changed. Might seem like a tautology, but I think it is. So here's a simple animation for you, if I can do it. Here we go. So the cube turns into the sphere, and the sphere turns into the cube, and they swap places. Has anything changed? Each of them has changed. We can observe it, right? You can see. Oops, you can see them.
You have to get out of this menu.
I've got a problem now. Yeah, I've got no. Okay, so I don't know if you want to see it again. It's just really, but it's kind of fun, isn't it?
We're going to loop.
Okay, so this is the consequence of classical particle indistinguishability. You have to say the state is unchanged, even though each of the things has changed, the state is unchanged. Okay. I don't think I've got time for this. I wanted to talk a little bit about Leibnizian methodology, but I think I'm just going to have to skip it because never mind. we all know Leibniz anyway. So I come back to the subject matter of this conference. So everything that I've given you is, you might think, just sort of boring old ordinary language, philosophy or something like that. Where's the structuralism in this? Well, Steve, I think, did remark on my discernibility stuff years back that, come on, Simon, this is structuralist because it's somehow the relations are prior to the thing or something like that. And I'm prepared to agree with, in weak discernibility, it does make it structuralist. Quine himself was kind of structuralist in the way he saw language, reading the notes, the structure's unchanged. I mean, I'm sort of with that. But it's not quite structuralism, and relations are very important. So I think it's good enough for structuralism, for structuralism, and in which case, fine, I'm totally paid up on structuralism. But in a way, there's a more deeper level at which I want to be a structuralist, which fits more with, going back to John Morrell's original motivation. After all, what is the continuity through major theory change? It doesn't seem to lie at the ontology level, but it does seem to lie at some other level. What is that level? So structure is supposed to be that level. But I think, and Warren originally said this, it's the mathematics that it doesn't not change, it does change. But clearly, dynamics anyway, but going right back to right up to today, is, I think, deepening, kind of enriching the mathematical structure, and a real voyage of mathematical discovery along with physical discovery, and there's real continuity to that. I mean, there's some discontinuity, but there's real continuity. So, I think in a way, that's the real deep structure of the world. And well, what happens to my ontology, made out of the level of words? Well, because I got this regimentation going, I'm talking about invariant predicates, I think it's a very interesting question, an open question for me, whether Maxwell would have been led to reify the ether had he done the sort of thing I'm talking about, namely being careful about invariance under symmetries. And it'd be an interesting question, what would be the symmetries? Presumably Newtonian symmetries, because he's looking at the mechanical ether. But it's the mechanical ether that gives rise to electromagnetic forces satisfying a Lorentz covariant system of equations. So right away, you'd have been alerted to a problem, kind of a mismatch, and it would have led to a kind of, whoa, hey, we're in a strange situation now. And actually, if he sort of, as he did, rather threw away the mechanical ether, but he still maintained that there has to be an ether. And if he'd looked at invariances of the electromagnetic field and tried to express, existence claims in terms of quantification over objects, I don't think they would have been bits of ether. I think it would have been space-time. I think that would be the only thing that would be led to invariant predication on the basis of the symmetries of the Lorentz, of the Maxwell equations. You'd be led to points as in space-time, not ether. But that, I don't know if that's true. I think it's worth some thought. So there may be, in other words, a case for continuity through major theory change at the level of the ontology that I'm talking about. Okay, at least ontic structuralism. But I think there's a deeper continuity at the level of the equations. And now what about that? What about the world as a system of equations? And I'm back to quantities as being fundamental. And notice I've replaced Aristotle by Plato, because I think the way we're in a slightly different realm. And I think the main thing I want to say, and this, I thought it may connect to Jonathan's ideas about monism, but I think in a way, there's almost nothing you can say about the reality of the world as quantities. I mean, I can't even say what is the magnitude of a quantity. Ratios of quantities isn't enough. I can't express it. I can write down the equations. I can talk about equations. That's no problem. But how to express the fact that reality is the system of equations, I think it becomes inexpressible. And I don't know if that's monism, but I think it maybe connects more with Parmenides and that tradition than mere priority of the holistic thing. It's something more than that. And maybe it's entirely appropriate that I'm inarticulate about what deep reality is. The best you can do is, as I understand it, is do the kind of thing I've been doing. So maybe people can do better. But I think what I've been doing goes pretty far in terms of a domain of exploration and discovery, which is, I think, what scientists think they're doing. Okay, so thank you to Fred. You're a wonderful conference, Fred, and I know how much work is involved, not just in organising the thing, but getting the funding for the thing. Brilliant. Thank you.
seriously now. Carrie is the first, second, Manali. 4? No? Okay. 5, Dylan.
Thank you so much, Simon. So I've got a bunch of questions, but really I'll ask this one. So is there any room for an analogy here between the permutation postulates? In quantum mechanics, the older states have to be permutation in their course.
Carrie, speak up a bit.
Yeah.
Sure. I don't know if it's called postulate, but Invariant Saunders. I'm sorry. I thought I'd turn my phone off.
Really? Is that your ringtone, Simon? Really? I have lost all respect for your view, your talk, everything. Sorry.
I didn't even choose the ringtone.
Oh, yeah, that's what they all say.
That's what they all say, yeah.
You know what I mean? So the permutation postulate, the new states have to be symmetric or antisymmetric. So given that you are saying here that there's an arbitrary expression can be equivalently expressed,
Yeah,
in a permutation variant form.
Yeah, as long as it doesn't use proper names.
right? Is there room for some like an analogy between like the Chrétien objection is to be more
Oh, sure.
but it turns out to just be a
I've
trivial,
never
but
thought of
every
that
theory
before.
has this
Yeah,
property.
yeah,
We thought
yeah.
that it had this really this profound physical property.
That's a very nice parallel. I hadn't thought of that. I think it. Yeah. I think that might go far. Yeah, it might well go far. I mean, it's certainly. Others, John Satchel, for example, has drawn attention to the parallels between morphism symmetries and permutation symmetries. It's the sort of separating analog, stuff with the things between relations. And yeah, that is actually pretty universal for any dynamical spectrum theory. And I'm saying it's pretty well universal for anything expressed in the calculus without names. Yeah. Well, thank you for that.
Okay, Manali.
Just wanted some clarification. Well, I guess two things, but first, I just wanted to ask for clarification. When you said that we are particulars, or we are indistinguishable.
Yeah, we're
And then-
indistinguishable people.
And you gave the example of bare particulars, and if we swap bare particulars or whatever, then
That's right.
we're still the
that's right,
same.
That's right.
But
The question of which pair particular is the one that has your properties as opposed to the pair particular which is the one that has all my properties is empty. We identify permutations.
yeah, so I don't know if you meant this statement to also include or to sort of exclude the possibility of something like, mind-body property dualism, because if so, then it would seem like there's still a difference even if we swap bare particulars, because there would be something like maybe a subject property that cannot swap and still be the same kind of entity. Did you have that in mind as well, or were you just thinking in purely physicals?
I'm really looking at just a match, a correspondence between what's happening in the state space structure of indistinguishable particles and quantum theory and in classical system mechanics, and what happens in the state space structure of the predical calculus. Because in a sense, the predical calculus gives us a state space structure where proper names play the role of sequence position, and when in indistinguishable particles, we're talking about particles, they all have the same mass, they all have the same intrinsic properties, exactly the same intrinsic properties. So you and I may have intrinsic properties which are exactly the same. As long as that's the case, then we're like indistinguishable. If, though, we have intrinsic properties that differ in some way, and we're talking about swapping those, but it's meaningful to say which, if this intrinsic property is clothed with all of the properties that you have, as opposed to the intrinsic property that is clothed with all the properties that I have, then there would be a difference. Indeed. So sure. It only the parallel only goes so far as you've got everything that's relevant that is describable in the predication. And of course, in normal toy models and predicate calculus, we never do that. And that's what justifies and legitimates viewing particularly in ordinary uses of predicate calculus as each being distinct from each other. And where it does matter, whether I'm saying that, it's you that's sitting in the chair and me standing in the lectern or the other way around.
Okay, good. And with respect to your comments in the very beginning about thudding disagreements,
Yes.
right, so you mentioned yesterday that you want to see someone show that
Yes.
a scalar field will clump up into some localized
That's right.
distribution,
Yeah.
but
Typically and generically that happens. Yeah.
typically generic, right? But now, what do you think of this? Because it seems like you could also have cases where even though the field variable doesn't clump up, it doesn't become localized, the magnitude of the field. So you have a delocalized field, but the magnitude of the field differs significantly in some sub-region of physical space.
Absolutely. That's what I meant by clumping. I didn't mean
That's
that
what
the
you-
field sort of ceases to exist outside of some domain. I just mean it's like small or vanishing or small.
Okay, but then if that's the case, I can give you a worked out example where that happens in at least pilot-like approaches to scalar QED.
Okay,
And
okay.
5/4 field.
Okay, we'll
Just-
meet. We'll meet and talk, and you're showing me. Okay. Yeah. And one of us will fall down. I hope it's not me, but I don't know.
Okay, who was number 3? Stephen, I think.
I thought I was number 4, but
I
okay,
was
me.
four.
Okay, so it's me. So this is really
We're in six.
to yeah, so exactly. This is to really invite you to say a little bit more about the inexpressibility at the end, and to ask, put it in the form of a question. Do you think that's a failure of, with all due respect, Jonathan, metaphysics, current metaphysics? Or, so for example, a Humean structuralist might say, well, I can express the idea that the world is just a system of equations, or the world is just law, because for me, law is just regularity. Now I've got to do some fancy dancing, right, to get symmetries in there, and maybe have to incorporate, fancy dancing, right? But I can express it. So I was just wondering why, although I'm sympathetic to this inexpressibility claim, I just wanted to try and pin you down a little bit more about what you saw as the origin of that inexpressibility.
Yeah.
Given that the Humean is over here saying, dudes,
Yeah.
I can express it, why can't you?
Yeah. I mean, I think in a way, there's a couple of things that I have to say. One is that I'm really skeptical about this best fit.
Right.
The idea that this Humean tapestry, and I'm trying to generate a Humean tapestry, but it's kind of just description of what happens. The idea that uniquely allows you to determine what the equations are. I'm just very skeptical as to how that will go, and I think what it would amount to is something like a way of articulating what a mathematical equation is in terms of what it would be. I'm going to go from the piece of the tapestry to an equation and back again, and I can talk about mathematics. We can always talk about mathematics. So I guess what's at issue is they'll go from the Humean tapestry to talking about equations. But I don't know that talking about equations is a way of talking about reality. That's part of the problem. I just don't know how that's supposed to work. I mean, indeed, in a way, what they're committed to is the equations isn't a way of talking about reality. The way of talking about reality is the Humean tapestry, and it's just that somehow that Humean tapestry uniquely picks out a piece of mathematics. But I don't think a Humean would say there's something over and above the tapestry.
Right.
So in that sense, they just stick with the tapestry, and the equations is a way of codifying that tapestry in a simple and economical way.
Yeah.
So, I'm not sure. Maybe I shouldn't be too quick to dismiss it, but I mean, it does seem to me that a very important part of what we're always doing is, what is the difference between mathematics and physics? What is the difference in physical reality and stuff? And of course, if you're really going to be saying that the mathematical stuff is somehow out there, and I do feel that in a way. I actually do feel that, but I don't really know how to say it. It probably better be the invariant mathematical, but then that's a problem as well, because how do you define it? You can define individual quantities that are invariant, but a whole mathematical structure which is nothing but invariant. I mean, the only way I can think of doing it is the way I'm doing it at the level of objects. And ontological structure realism. And I don't think that's what. Right, sorry.
Yes,
As
no.
much sense as I can.
Sure.
Right.
Yes, could you go back to the slide where you just mentioned GMW? On the bottom you have this
Did I?
sum of anti-symmetrized terms.
Yeah, right.
I don't know if this will end up being a question
Yeah.
or comment. Or,
Yeah,
yeah, I think so.
yeah.
Because you said something like, well, once you get superposition, it will be interesting, but without superposition, they're just anti-symmetrized separable states, right?
Yeah, but this is also interesting. I mean, when saying there are n things and each has its state, and that state is very informative, and so we're saying quite a lot. But the thing is, what blocks a totally clean interpretation of the ontology of quantum mechanics is genuine entanglement.
Yeah.
Because once you've got superpositions of states like this, I can no longer say there's just n things. I
Yeah,
can't
so-
say that anymore. All I can do actually is.
But I think so I think in mine except it already happens without taking superposition, right?
Well, according to you, you've got violations of inequalities even without taking superpositions of these things.
Because
That's
I think what's happening is that the state I mentioned has like two particles with spatial wave function L plus R,
Yeah,
and one is spin up, one spin down.
yeah,
So of course you could interpret this as, oh, we have two particles, they both are in superposition of left and right, and one is spin up and one is spin down. But when we measure, we're not measuring particles which are superpositions of left and right. We measure particle on the left and particle on the right. And in that language, you can say, oh, we have superposition of either two particles on the left, up, down, two particles on the right, up, down, or one left, one right, single state. And that's why you can violate the law.
yeah. I mean, sure. And of course, as an Everettian, I will also understand the measurement apparatus as entering into the entire entanglement. So if you ask me what's fundamentally going on, I'd say that.
Yeah.
And of course, notice that when you've got macroscopic superpositions, then I think we do have a way of articulating what's going on in terms of parallel realities. Strange as that may seem, so we do have some understanding of articulation of that. We've got the concept of distinct times. I think we can have the concept of distinct worlds. But no, sure. I mean, I really have to look at what you've proven to understand how this impacts on what I'm saying. I was giving this deflationary account. Maybe it can't be as deflationary as I think. If guys like this can already lead to bell violation, then I'm surprised. I don't know how energy it is to what I'm saying.
Maybe not sure. Well, I don't know.
Anja?
I think Jonathan was before me.
Oh, John. Okay, go ahead, John.
Thanks, Sam. Could you go back to the Buckley slide?
Yeah.
So I thought the inexpressibility stuff is really intriguing, and maybe what I'm asking is going to go in that direction. I'm not sure. I was surprised to see you go with something like a Ramsey sensor, an existentially quantified thing, as the way to express permutation and invariance. I guess I'm thinking that in standard semantics for the existential quantifier, it's going to just draw on a pre-existing domain of individuals. When I have a pre-existing domain of individuals, I can easily define up names and just not make that move, but it's there to be had. And moreover, I guess I also think that existentially quantified claims are made true by their instances. You think of the existential quantifier as something like a massive disjunction, and the disjunction is made true by its true disjuncts. So I guess I wasn't thinking that the existentially quantified claim was a perspicuous expression of permutation and invariance, but maybe we needed maybe we need a connection of descriptors, or maybe we need to go to like a predicate functional language to really have a quite different semantic apparatus that's not presupposing background domains, individuals against which permutations still seem to make sense.
Right,
Why
right,
is
right. So,
that
well, just
represented?
a couple of things. First, it's not the existential quantifiers expressing permutation events, and what's expressing the permutation events is the symmetrization that I've done at the level of the predicates and their names. It's simply that, you know, what if one dispenses with names? If you dispense with names and you just write down something like this, and it's not special, but I mean, I don't think it's, the existential quantifiers are kicking in there just because I'm getting rid of the names. That's all.
But even with the disjunctive formulation, there's still the thought that well, first of all, there are names, so
Yeah,
we do
right.
have individuals.
No, no,
And
it's-
secondly, the disjunction, I would have thought, is made true by its true disjunct. So if that's true, one of the disjuncts is true, and that's why
Right,
the disjunction
right,
is true.
right, and
So I still don't feel like this is getting
Yeah, yeah.
away from.
Yeah. So the way I'm thinking about this is that go back to Gibbs, you know, that in thought we can individuate everything. So in the level of the model theory, sure, we've got you know, different models that make the sentence true. You know, so we've got two different models. One way of saying that the concept of reality that is operating here is a semantic equivalence class of the models and the permutations, which is sort of common unit. And I think that may well be right, but I mean, I think the point is how do you obliterate the distinctions in the model that are available for the having, you know, just by virtue of being a set theory.
And you can obliterate the distinction technically by taking an equivalence class. But
Well,
then what does that mean?
Right. But I think another way is dispensing with the names, because if I have this and I don't use any names, I can't express the thought that that I've interchanged the two. I mean, I just can't say it. But maybe this is more obvious actually at the level of my at this thing. You know, the way in which we could express the fact that the final situation is different from the initial situation is because I can say that the initial situation, this one is A and this one is B. The final situation, A is cubic rather than spherical. So I can express the distinction. But if I don't have those names, I can't express it. And that maybe is enough, you know, that just to forego the use of names is enough already. You don't have the wherewithal to express the kind of permutation that's an issue.
But the question is what kind of, the worry is that the ongoing use of existential quantified semantics, you are sort of optionally foregoing the use of names, but
Yes.
you've got a semantic apparatus running in the background in which one can simply introduce names if one chooses. It's
Well,
well-defined name.
Yes, but I'm just saying, that in the model, you've got, in the set theory construction, you've got exegetes, if you like. And you can use those exegetes to introduce names and give yourself the expressive wherewithal to distinguish the initial and final states of these two things. And in doing all of that, you're exactly breaking the discipline. In a way, it is a discipline, just what can be said, what can be expressed without use of names in terms of what the quantified statements. And you know, that is the parallel to what's going on in quantum theory when you use totally symmetrized random symmetrized states. So I'm sort of just trying to copy the structure in quantum mechanics in ordinary language so that we can better understand what quantum mechanics is telling us. Then to be told, well, but now in ordinary language you've got this stuff, you've got a set theoretic model, you could now introduce names if you want to, and now you can articulate distinctions that can't be drawn at the level of the symmetrized state, is only to say, yeah, sure, but it's just broken the thing that I've carefully and, painstakingly built up. Sorry. Yeah, but so it's so easy to do, and like, right, in a way, I think, why, if I'm right about this, it's why it's taken a long time to get here. It's more likely that I'm wrong, you know, I really
First, Anja.
Thanks a lot, Simon. I wanted to ask you about the moral of your talk and see if I could press you to give us a little bit more detail. Specifically with respect to what you wanted to say about the nature of the realist project or your project. So you said a number of things throughout your talk that suggested parts of science or thinking about the upshot of scientific theorizing and modeling that have epistemic significance, right? And we think about scientific realism as some kind of diagnosis of the epistemic significance of our best science, right? So, you know, what are some of those things? So there was the nice idea of common sense bodies being conceptually fundamental, presupposed in our talk of all sorts of other things, right? That may be shared by Quine and Frassen and many others. There was the idea of exploring a domain. There was the idea of articulating things with words in a way that, when you're exploring a domain, you can talk about these things in a way that's continuous with the everyday or common sense objects, right? There was even the idea at the end of, you know, there's got to be something to the idea that there's a continuity of mathematical mathematics, right, over time. Now, all of those things strike me as having the character of necessary, at best necessary conditions, right, for realism. But not any one of them being sufficient, and not even jointly sufficient for realism. Because if you think about all of those things, I don't think you find anyone that disagrees, right? So an idealist is going to agree, a constructive empiricist is going to agree, varieties of instrumentalism are going to agree, and of course realists are going to agree, right? So as a conception of the nature of the realist project, it feels currently underspecified, right? And if it turns out that what might make the difference, what might provide the sufficient condition for taking us from this generic picture to something that's more realist sounding, if what's required is expressing something that is inexpressible, then I'm not sure we have a conception yet of realism.
Good.
So can you say something more about that?
Yeah, absolutely. Well, I mean, using the tools that I've been talking about and using, I guess, I think we can get down in the special sciences to virtually everything short of individual atoms at non-thermal absolute zero. We can get to molecules, viruses, we can get to all of that stuff through talk, continuous with talk of everyday objects. I would say anybody who's engaging in that sort of talk and wants to be taken seriously in what they say is ipso facto someone committed to those objects, the viruses, the molecules, and so forth. So in a way, I think the question becomes always the foil is Van Frassen. Van Frassen's stance is, first off, I don't think he would engage in the talk, but if he did engage in the talk, then Baz, why do you say this stuff if you don't take it to be so? I mean, you say it and then you call, but I'm agnostic about whether what I've said is true. I'm saying it, but I'm agnostic about what I just said. And if you look at Quine and what there is in that whole tradition, it is that, you know, you've got to stand by what you say, it's not to take it seriously. If you don't want to commit to something, then just don't talk about it. So in those ways, I think it is a realist program, if you like, and anybody who's prepared to engage with it ought to stand by what they say.
Can I? So I think a lot of weight is perhaps born in what you say by the idea of taking seriously the talk. Right? And of course, there's a realist way of reading what it means to take seriously the talk. And sometimes I think it might be unfair of us to say to a constructive empiricist or a Noah, or for that matter, a logical empiricist, to say, to the extent that you're using this talk, you're not taking it seriously. In fact, I think that that's probably just incorrect, right? I think they are taking it very seriously. It's just that they don't interpret it the way that we do. They take it seriously and then would characterize the epistemic upshot of all of this talk in different ways, right?
Okay, so let's look at real examples, shall we? Look at Carnap, and of course, Carnap's way of saying not taking it seriously is to say it's analytically true, within the framework. So that was a very important device. Without it, I think Carnap would have not had a good comeback to Quine. Of course, for Quine, it wasn't a good comeback because synthetic distinctions could be motivated and poorly defined. So that was one way of not taking seriously what you say by virtue of embracing the risk and so forth. Are there others? Well, sure. You know, there's fictionalism. You know, there's other sorts of moves whereby people could not be taken seriously in what they say. But interesting, I think, about Baz van Fransen is that he would I think just reject the whole enterprise of trying to articulate in words what exists. You know, and why was he so adamantly opposed to any preoccupation with language? Remember this in the scientific images. It's a great mistake of 20th century philosophy of science. It's preoccupation with language. And he spoke about you hold up a data set, you know, for inspections where you don't assert anything, you sort of hold it up. You know, he's getting away from language. I think this is in a way how he deals with. He doesn't want to be taken seriously in what he says, so he doesn't want to say it. You know, and the theory is not articulated in language. I'm with him there. For him, it's articulated in models. I'm sort of with him there, but I want the models to be equations and things like that, and paradigm examples, applications of equations. So he would, I think, just draw the line and, you know, okay, maybe you have to say stuff about observable things, but you don't have to say stuff about non-observable. The one place where I find it very problematic is when it comes to explanation, which he does take to be avowedly linguistic. So I don't really quite get how it's okay to explain, you know, gas laws in terms of movements of particles, macroscopic particles. There it seems you're having to say something, you know.
Well, sure, but then, you know, it's a pragmatic conception of explanation, right? So, I mean, I don't disagree with what you're saying about Van Fraassen, but I do think that when we say that, you know, even take an extreme example, take the fictionalist, right? I do think that we're employing a realist conception of what it means to take something seriously when we say they're not being serious. Because, of course, using a theoretical vocabulary in order to give economy to your manipulation of concepts so that you can do scientific work and communicate with one another is an entirely serious enterprise, right? So that's why I worry that we don't yet have a realist project articulated.
But can we just think about goals of science? You know, the idea that, I mean, for me, the goal of science is really exploration, discovery. So that's a fairly, in the micro work, as much as in the cosmological. So that is the goal. It's a very clear-cut way of distinguishing those.
Sure, but last comment, I promise, which is to say that I think that, you know, in contemporary discussion, a number of people have retreated to that, right? So what do we mean by realism? Well, it's something axiological. We have a goal, we're aiming for the truth, we're aiming to uncover something. But of course, you know, that's so weak that you might wonder whether it merits the label realism. Because of course it's consistent with the idea of never achieving the goal. It's consistent with the idea that we're nowhere close to the goal now, not even approximately or partially. It's consistent with anti-realism.
Yeah, but hang on. I'm talking about discovering, exploring. It's not an unachievable thing. We're doing it all the time.
Well,
You know,
okay, but
I'm
now
not
you're
talking
going
about
beyond.
truth.
But now
I'm
you're
not
going
talking
beyond the
about
goal, right? Now you're going beyond the
Well,
goal.
I don't know if I am. I mean, the goal is
Well, if you're achieving
exploration.
your goal, you've gone beyond merely having a goal.
Well, the enterprise is exploration. And there's no limit to how far this exploration will go. It'll go as far as we can go. You know?
Sure, but no one would disagree with that. That's all I'm saying.
But the exploration is of the domain in the micro world at the level of unobservables. No anti-realist would embrace that as what we are doing. They wouldn't call it exploring a domain at all.
Okay, last question for Mike.
Well, it was really to revert to the early discussion about what is presupposed in assuming set theory as the kind of ontological hinterland behind quantification theory, and how that, which brings with it, it seems to me, essentially the name-bearer relation-based Fregean understanding of objects and the external quantifiers. I mean, how that is obviously radically affected by looking at this situation of symmetrization of the state space, the situation you have in the indistinguishables, and what kind of machinery coming from predicate functor representations of the language could possibly replace that understanding of the quantifiers. But it's probably taking us too far afield, so perhaps we could reserve it for private discussion. I think there is a, I mean...
When I'm quantifying other things...
Well, this is the thing. I'm not so sure that you any longer are quantifying other things when you get to the position here that you're having to give up the very background assumption about the name-bearer relation, about set theories as were being available as the kind of ontological hinterland of quantification theory, which...
Is what gives content to language and discourse.
Not in general, but in the case of in the case that we have the understanding that we are picking out an individual member of the domain, and the domain consists already of things the same or different absolutely to be the value of the variables, which seems to be what is undermined by the example of the indistinguishable particles. Surely that is part of what you're assuming. Okay.
Yes, but Mike, can we speak about it?
Well, exactly. That's why I was saying I think we should reserve it for another
James has
time.
questions.
Yeah.
Okay,
Trying to
James.
ask you to what?
So my question is about the relationship between different kinds of discernibility and proper names.
Yeah.
So I was just wondering what's really the significance of proper names or not. So if you have a language without identity and you have no proper names, but everything's weakly discernible, at least weakly discernible from everything else.
Mm.
Then if you add proper names, you get absolute discernibility.
Yeah.
Yes.
So, do you want to comment on that? I mean, what? So do the proper names really matter? I mean, what? Like,
I mean,
yeah.
the use of proper names, and we're seeing it in adding them to the discernibility automatically gets strong. It's just to say the use of names gives you an expressive competence without them you don't have. It gives you something that you can articulate, which without proper names you can't do. I mean, in practical matters, we can usually talk about some stable dynamical property and use that as a proper name. And, you know, fine, that works where it works. You know, and going down into the quantum, why stick with weak discernibility? Why don't we talk about the one particle state? You know, so the answer being, well, a one particle state isn't something that could have other properties.
Yes. You don't have the stable dynamical properties.
Right, the one
Yeah.
particle state is not, well, it's not compatible with other dynamical
Yeah,
properties that
exactly.
we have. So it's sort of useless to function as a proper name does in ordinary predication. Because in ordinary predication, the point is that the proper name is stable with respect to all the predications we care to make about it. Right? But when it comes to it, when you really look at what that proper name is grounded on, and I see it as grounded on a stable dynamical property.
Yes.
In the macroscopic world, sure.
Yeah.
It's stable enough. You know, our DNA is just great, totally stable. You see what I'm getting at? You go down into the micro world, and there's really nothing that is stable in these ways, and there's just no basis on which to make use of it. This is why we really end up with weak discernibility.
Yeah.
You know, it's the only way
So I
one
think
can
my point
articulate
is it's that
just
only weak discernibility that's really crucial rather than the lack of proper names. Because if so, as you say, you don't have absolute discernibility
right.
without names and the identity relation,
Right. Or stable dynamical properties and talk about that.
which you could use. But if you do have at least weak discernibility,
Yeah.
then you can add names and then absolutely discern everything, or not. But it doesn't change the metaphysics, as it were. Right? The system just is what it is. Everything's weakly discernible from everything else. It's just a matter of how you refer to things.
But the thing is that I mean, you don't just introduce names as a sort of by fiat.
Yeah, exactly.
It's not like that. I mean, you're trying to talk about reality. You're trying to really talk about these entities, and I mean, just calling them Bob and Charlie and Flora or something. I mean, because you've got no criteria on which to apply that name. I mean,
Yeah.
you
There is no
phrase
fact of the
makes
matter
sense.
about which is which in the case of the.
Right. I mean,
Yeah.
it just doesn't have a usage. So, and how do we ever get to talk about things? It's really difficult. It's really complex. I mean, all that stuff that Quine wrote about this, I don't know whether that was Armichael or not, but some complicated story is going on about how we master language to the point where we can start to refer to real objects. It's really difficult. But we do it.
That seems a profound ending enough. So, thanks, Simon. We start again 10 minutes before